This is Dr. Kraus. It is Monday, September 15th. This is the first lecture I'm posting to make up for my missing class today. What I want to talk about is one really good way to start making sure you understand what we're learning about the FFT and also preparing yourself for the quiz 2, coming up a week from today, Monday, September 22nd. And so the thing that I want to show you is I'm going to post this Python file. It's going to be called FFT for quiz2.py. And what I want you to see is connections between the choice of CAPT, the choice of FS, the sampling frequency, and then the symbolic expression for Y. And how does that affect the time domain plot, but more importantly for us, how does that affect the FFT plot? And so right now we've got a CAPT of 1 second that's going to lead to a DF of 1. And so our frequency vector is going to go 0, 1, 2, 3, 4, whatever. And then we've got a sampling frequency of 10. And since our frequency vector stops at Fs minus DF, it'll go 0 to 9 in steps of 1. And our cosine wave is at 1 hertz. So we ought to expect to see something at 1 hertz. We ought to expect to see something else aliased. And so let's talk about that. So I run this thing, and here's my FFT, and I do see a peak with a value of 1 at 1 hertz. And then I also see this aliased peak at 9 hertz, also with an amplitude of 1, and I see a cosine wave. And then I've made the code print out the F, A, and B vectors. And you can see that the B vectors corresponding to the sine terms are all 0. The A vectors have a 1 that corresponds to 1 hertz, and then an aliased 1 that corresponds to 9 hertz. And one of the things I want to show, I'm going to switch this over to a case 2. We're not changing anything except we're going to 9 hertz instead of 1 hertz. And what I want you to see is that exactly nothing changes. The A vector remains the same. Now we happen to know that this 1 at 9 hertz is the non-aliased and the 1 at 1 hertz is the aliased. But from a digital perspective, looking only at these graphs and the results of the FFT, they look identical. Case 1 is identical to case 2. If I flip this back to case 1 and rerun the code, nothing changes. The cosine wave looks exactly the same. The FFT graph looks exactly the same. The A and B vectors look exactly the same. And one of the things I mentioned in lab the other day, I think the first step in getting this kind of a question right is to come in and say, okay, what is my frequency vector? Once you know that, then you can say, okay, where do I have symbolic components? Where do their non-aliased terms go? And where would the corresponding aliased terms go? Then, for example, if I were to come in here and change this to 2 hertz, now my DF is 0.5 instead of 1. So my frequency vector got a lot longer. There are now more elements in my A vector and my B vector, but they're all zeros, and the number of non-zero elements doesn't change. I now have 2 periods of this cosine wave. I now have a little bit sharper looking peak because there's a 0 point here and a 0 point here at 0.5 and 1.5. And I have a term above my alias term at 9.5. But otherwise things are the same. And again, if I switch this back to 9 hertz instead of 1 hertz, nothing changes. So as you play around, if I went to 1.5, for example, I now see that I have 1.5 periods. My cosine wave is not periodic in my time window, and so I get all of this leakage as I've got terms that are non-zero that are kind of all over the place. And then, for example, if I come in here, well, let me do one more thing. Let me make this case 4. We'll talk about this in a second. Let me duplicate case 2. But I also want to make sure that I think I already posted something about this. But if this were 1 hertz and it were a sine term, We came over here and ran, make sure that case is set to 3. It's not. Okay. So now when I run it, I've got a positive sine wave, but I'm seeing a negative peak at 1 hertz on the FFT graph. And then if I were to talk about an aliased sine wave, so we'll make that case 4, we'll make this case 5, we'll make that 9, and we'll run case 4. Now, because of aliasing, and because of the complex conjugate nature of the sine terms, this graph's changed, but it only changed in its sign, its SIGN, and got multiplied by -1. It still looks like a 1 hertz sine SINE wave, but it's multiplied by -1. But even though this looks negative, the FFT at the 1 hertz is positive, so this is the lower ones are always the opposite of what you'd expect. And then it's a -9 hertz. So that flips over as I go back and forth between cases 3 and 4. Now this looks like a positive 1 hertz, but I see a -1 at 1 hertz and a positive 1 at 9 hertz. Okay, so if I understand those things and I understand how to find the frequency vector and I understand how to do FS and all that kind of stuff, then if I give you something like this symbolic expression, y is equal to 3 times the cosine of 2 pi times f1 plus 5 times the sine of 2 pi times f2, and I run this thing, and so what we should expect is a peak of magnitude 3 in my a coefficients at f1, and then also aliased to fs minus f1, and then a peak of magnitude -5, because this is positive, at f2, and then a peak of +5 at fs minus f2. So let's run case 5. And so the time domain signal now looks pretty messed up because we don't have that great of sampling. But what we do in fact see, what I want to be clear about here, is that we do have a magnitude 3 peak at 1 hertz in the a coefficient and at 9 hertz in the a coefficients from the cosine term. And then we have a magnitude -5 peak at f2, which is 3 hertz, and a magnitude +5 peak at fs minus f2, which works out to be 7 hertz. So as you play around with different combinations of y's and fs's and df's and all those things, you can start to think about how to correctly answer questions like, given a certain symbolic y, how do I find the a and b coefficients? And again, for that case, with the 3 cosine of 2 pi times 1 hertz plus 5 sine of 2 pi times 3 hertz, we see this result. And so I will post this video along with this code for you to play around with. I'll also post the example quiz that I showed in class the other day. And you could use this code to try to investigate the answer to that question and come up with new questions on your own as you're trying to study this material. Thanks.